Hi, folks. Welcome back to another Rider webinar, actually the first of the year. So thank you for joining us today. I'm really excited. I was just talking to our guest in the green room. I guess that's what we call it here. But yeah, I'm really excited to have him today. But before we get and introduce our guest today, let's do a little bit of housekeeping. So first of all, thank you for joining us on YouTube. If you're watching this live right now, and I know a lot of people are, I see the chat is really excited today. A lot of people are saying hello, hi. If you have any questions throughout this webinar, please feel free to ask in YouTube. I'll be cataloging all those questions, and we'll be asking our guest at the end of his presentation those questions to get those answers for you. So one common question that always comes up during these webinars: hey, is this webinar recorded? Yes, it is. You can watch this YouTube video later on JetBrains TV. So if you need to drop off for any reason, or just want to kind of rewind and see something that our guest showed again, yeah, you can catch it on JetBrains TV. So yeah, this is recorded and you'll be able to watch it later. So on that note, let me introduce our guest today. Our guest is Aaron Stannard. Aaron is the CEO and founder of Petabridge, where he makes distributed programming for .NET developers easy by working on Akka.NET. He's also worked on NBench and dozens of other open source projects. Aaron is also the founder of SDK Bin. So if you're doing any open source projects that looking to maybe do something like dual licensing, where you can kind of sustain your project, check out SDK Bin. Think of it like App Store meets NuGet. Is that correct, Aaron?
That's right.
Yep.
We should be available for third-party publishers later this year.
All right, very cool. Yep. Thank you for coming on. I'm really excited about today's topic because, yeah, distributed programming is always one of those things that's can be very challenging, and frameworks like Akka.NET can definitely kind of smooth out a lot of the issues that typically come with that. So again, thank you for being here today.
Oh, it's my pleasure. And thank you for making such great products. Been a ReSharper user for many years, and I've been using Rider as my full-time IDE since 2021. So always happy to support a company that makes great products.
Oh, excellent. Thank you. Thank you for those kind words. So on that note, I'm going to pass it on to you. I'll be here checking the chat, gathering questions, and I'll give you the stage now.
That sounds great. So today we're going to be talking about .NET Systems Programming Learned the Hard Way. Now, to give you just a little bit of background about me beyond what Khalid mentioned. Akka.NET is a highly concurrent distributed actor model implementation, although we also do local in-process actors. And what this means is that our users really kind of pay a premium for trying to maintain low latency, high throughput, and low memory consumption. So, I've been a .NET developer since 2005. I first started learning .NET when I took an internship to work for the Fair Isaac Corporation. They're the people who develop your FICO scores. So I kind of learned .NET 2 there. FICO scores in the United States is what you use to get approved for a mortgage. It's basically your credit rating. I've also built large-scale software as a service on top of .NET. Did that back in 2012, 2013, 14. And we're also still developing some of that today. And I've been the maintainer of Akka.NET for going on about 10 years now. And I've had to deal with, let's say, hundreds of end user applications and performance problems that have come up. And that's kind of my everyday, is dealing with these infrastructure type problems that show up for .NET users that are doing things in spaces like finance or IoT or energy production or doing real-time pricing. Think of things like high-frequency trading, for instance. So we see a lot of different types of applications. They all vary by industry, but they all have common problems, which is that they're mission critical and they need to be real-time, which typically means low latency and being able to support that low latency guarantee across an arbitrarily large number of requests. This means that performance is kind of key to a lot of what we do around here. And so we're always treating performance like a feature inside our development. And this leads us to need to learn how the internals of .NET work in order for us to get the best possible performance out of them. Now, one thing I will say is that the .NET project team at Microsoft has been doing a lot of work to help give you a lot more performance out of the box without needing to know how to do lots of crazy low-level optimizations. This comes about in the form of new language features, but also in more kind of free lunch type things like just-in-time compiler improvements, such as the dynamic PGO they added in .NET 7 is a good example of that. And this also can come about as a result of garbage collector improvements too. And that's the first place where we're going to go ahead and start, is talking about the .NET GC model and the impact this is going to have on your application from primarily a throughput standpoint, but also to some degree a memory management standpoint as well. Now, the way .NET garbage collection works is it's a generational garbage collector. Primarily, we're going to go ahead and just take a look, without considering the generations part, of just how GC works in general. An application is going to root certain objects when there are active references to them at any given time. So if I have, let's say, these 7 objects in memory right here, and 3 of them are, let's say, this diagram is not exactly one-to-one, but let's go ahead and say 5 of these objects are currently being used right now out of the 7 that are allocated right here. The garbage collector can detect which objects are no longer rooted, and it will reclaim those and reallocate that memory. Now, the process of garbage collection works by taking a look at different generations of objects here. The cost of collecting an object is correlated to how long that object has been rooted to some degree. And the reason why is this key term right here, compaction. Imagine if we go ahead and we deallocate object 2 and object 6 without performing what's called memory compaction. We would get what's known as memory fragmentation when this occurs, meaning that we'd have this free sector here and this free sector here. And in order for us to take advantage of that memory, the next time we want to allocate an object, we'd either have to break that object apart. So let's say you have an array. That array would need to have some units allocated in the previous space object 6 occupied, or in the previous space object 2 occupied. And that would mean that when we want to go and access that memory, we would have to access it non-contiguously, which is going to be slower and means that we can't necessarily take advantage of things like caching in some areas here. So what the .NET garbage collector is going to try to do is compact that memory. And this is where the generational approach to garbage collection becomes important. Gen 0 garbage collection is, Gen 0 and Gen 1 are what's known as ephemeral garbage collection. This means that if you're looking at the .NET heap, which is where your objects are typically allocated, these objects are allocated right on top of, let's say, long-lived memory for your Gen 2 or large object heap objects. And if I use this memory for a very short period of time, it's very inexpensive for me to compact it because I'm essentially popping it off the top of the stack. So that's why Gen 0 and Gen 1 have a very negligible GC cost and basically don't really contribute much to memory fragmentation. So Gen 0 would be an object. Let's say if you declared an object inside a method and then that object was no longer rooted once that method exited, that'd be a good example of a Gen 0 object. A Gen 1 object might be, imagine if you had, let's say, 2 different classes that both passed around a reference to the same object, but that occurred in a fairly tight scope. A Gen 1 object would probably survive 1 or 2 rounds of Gen 0 garbage collection, but it wouldn't survive the number of rounds it would need to be in Gen 2, where Gen 2 is for very long-lived objects. Imagine an object that's being passed around lots of different await statements. Let's say if you're doing a big asynchronous process. That'd be an example of something that might get promoted to Gen 2 if there was, let's say, a scope that lasted for a fairly long time, maybe because there were some long-running I/O operations, or maybe there were a large number of awaits that were happening there. And then finally, we have the large object heap, which is kind of a special case. These are for objects that are bigger than, I have it in my notes here, let's see, 8,500 bytes, so 85K. These are objects that basically have very different, let's say, sort of behavior when it comes to compaction and fragmentation, and they tend to be set aside into their own little special area. So this is where, for instance, if you're allocating large buffers or maybe large object pools, that might end up inside a large object heap, for instance. Now, let me step through here. Now, the .NET memory model, in terms of how this works under the covers here. We have our stack, which are when you're allocating, let's say, value types like structs, integers, date times, time spans, that sort of thing. Those get allocated on the stack, which is thread local memory that is going to basically be dumped as soon as the stack frame exits. So the stack is essentially free allocations. As we've been kind of learning from the, let's say, some of the performance work, the .NET team has been sort of advancing through, let's say, the creation of things like spans and that type of thing. The stack is a fairly inexpensive place to do work. The managed heap, which is where garbage collection actually happens, is a little bit more expensive. So let's take a look at this piece of C# code here and see how this might translate into .NET's memory model. Well, I have my function, which itself requires an allocation on the managed heap. You know, all of your methods are going to have an address in memory that refers to the instance of that method for this specific object. One of the reasons why static methods are something that Rider recommends is you only need a single reference in the managed heap versus having one of them for every instance of an object. So there's an advantage there. And then we also have our little random object here. This is also going to be declared on the heap. And then finally, down here, we have our string allocation right before we write it to the console. That's also going to end up on the managed heap as well. Well, if we take a look at what this function does, we use our random class to generate two integers. We add them together, and then we write the results out to the console as a string. Well, what's going to happen here is that these integers are going to get allocated to the stack, so there's never going to be any garbage collection for them. This read-only random object, which uses random.shared, that's a static property that's built into the random class in newer versions of .NET. This is going to be in Gen 2 garbage collection, and it's never going to get collected until the process exits and all of the process's memory is reclaimed, at which point that's not your problem anymore. And this function will basically stick around in memory for as long as its parent object does. So this function might be, depending on the lifecycle of this object, Gen 0, Gen 1, or Gen 2. This random object will definitely be in Gen 2. And this string that we're allocating it, then immediately getting rid of it. That's probably going to be a Gen 0 allocation. So what the impact of this all is that generally speaking, the lower the generation of your, let's say, garbage collection generation, the less expensive it is to reclaim that object. It's cheaper to compact memory. It doesn't require the garbage collector to basically pause your thread and come back and try to reclaim, check the roots on objects that have been referenced by a large number of different other objects inside your system. So Gen 0 and Gen 1 are pretty inexpensive. So by design, you either want to try to keep your objects in Gen 0. That way you can go ahead and avoid memory fragmentation and make compaction less expensive. If you use value types, that's even better. There's no garbage collection overhead at all for doing that. And the impact on your latency and throughput is going to be a lot less noticeable. Gen 0 is much less expensive, probably by a couple orders of magnitude, than Gen 2 is. Now, if you have Gen 2 objects, now you're not necessarily going to be able to do this for every Gen 2 objects, but generally speaking, you want to keep Gen 2 objects available in memory forever if you can. This means using techniques like object pools, for instance. So if a Gen 2 object's available in memory forever, that means it's never going to get collected and you're never going to incur that collection overhead. On top of that, those objects will all get, let's say, compacted. Essentially, those objects might get compacted periodically when memory frees up below them. But by and large, they're going to be more or less stationary inside your application. It's not the fact that they're a Gen 2 object that makes them expensive. It's the act of collecting the object is what's expensive. So a good practice for this, for instance, is using the Microsoft.extensions.objectpool base class library. This is something relatively new that Microsoft introduced probably around the time .NET Core 2 or 3 shipped. And this is a library you can reference even in a .NET Framework application today. And this gives us the ability to create pools of objects that you can rent from and return to. And it's a great option for trying to prevent Gen 2 garbage collection. So the best candidates for something to go into an object pool tend to be reusable types. Probably the best example of this is going to be a string builder. You have your string builder, you use it to go ahead and format something you need to print out to the console, or maybe some other type of string you want to transmit as an output in an ASP.NET application. And then once you're done, you go ahead and clear its contents and stick it back in the object pool so it can be reused again. Byte arrays are another good example of this. You can use the same byte array over and over again for, let's say, reading content out of a file, or going and parsing, let's say, a large buffer you received maybe over the network somehow. You can reuse the same bytes over and over again by just, after you've deserialized your content, you can go ahead and just clear the byte arrays, essentially null it all out, and then use it once again to go ahead and read through the same, read through basically the next page of memory that's coming from your file reader, for instance. There's a separate type of object pool for this called a memory pool you can use for doing just this. Now, when you use a object pool, basically the object pool is more or less populated for you in advance. You specify how big the object pool can be. You rent an object from the pool, you use it, and then you return it to the pool upon completion. There's little APIs that are built for this. This won't cause allocations so long as your pool capacity isn't exceeded. So if I have 1024 string builders, as long as I'm not using more than that, we're not going to allocate any additional string builders. So one thing that the object pool will do is it'll periodically grow the total number of objects that are in there if you do exceed that. I'm not sure about every single implementation of this class, but it might possibly shrink it if there's some that aren't used over time. I haven't looked into the internals to tell you exactly if that's the case or not. But generally speaking, we tend to go ahead and kind of pad our object pools big enough to never be something that we're realistically going to exceed in our applications. This is a good technique for being able to prevent some Gen 2 garbage collection for reusable type objects. So to give you an example of the performance impact of this, I pulled some of Akka.NET's default JSON serializer code and put it on screen here. So we're using JSON.NET internally. And one of the things that we now do inside our serializer here is we fetch a string builder that we're going to use to take the rendered output from JSON.NET. And we rent it from the pool. We pass it into our JSON text writer. This is during outbound serialization is what we're using this for. So we do our work, and then we return the object to the pool afterwards. Well, here's what the performance impact of this looks like. This is using some benchmark.NET numbers. And this is what our, let's say, latency kind of looks like with pooling and without pooling. So without pooling, it takes us about 44.7 milliseconds to serialize. I think this is 10,000 or maybe 100,000 objects. I don't remember the exact count anymore. But the latency difference here was, I don't know, maybe 5% when we're doing it on a single thread. When we're doing it on multiple threads here, you can go ahead and see that the actual latency matters quite a bit. And on top of that, our memory allocation when we're pooling is, let's say, roughly 40% less than when we weren't pooling before. That's just the benefit of kind of getting rid of, 30% memory savings and eliminated 100% of, eliminated 100% of Gen 1 garbage collection. Yeah, that's for doing it in a single thread. And then in multi-threading, we had a 28% improvement, and we're able to eliminate probably, again, about 30% of memory usage here. So using pooling helps quite a bit. Now, the next big benefit of basically the .NET garbage collector is that it's highly configurable. So in addition to kind of being aware of what generations the .NET garbage collector uses, knowing how to configure it properly will also help give you some bang for your buck in terms of improving the performance of your applications. Now, the next slide I'm going to show you is probably the most valuable thing you'll get out of this entire presentation if you're not doing it already. So this is the good stuff. We have several different modes of garbage collection. There's workstation garbage collection, which is basically the default for most .NET applications. And this uses blocking garbage collection, meaning your thread gets suspended when the garbage collector runs. This is kind of old school GC, and it's appropriate for, let's say, console applications, the things that run on an end user's machine. It's not ideal for server-side applications, which is why we have server-side garbage collection, where garbage collection now occurs on dedicated threads, so it doesn't block your application's workload. And on top of that, instead of having one giant heap for your whole application, we now have a heap per core. So instead of having to do garbage collection for everything in Gen 2 in your application at any given time, we're able to do it on a per CPU basis. So if you have a server with 16 physical CPUs, not logical ones, you'll have 16 different little heaps, and those will all be garbage collected independently from each other. On top of that, just to make it a little confusing for everybody, we also have a feature that was introduced, I'm not sure when exactly. I think this might have been a later version of .NET Framework, like 4.6 maybe. But we have what's called background garbage collection, which actually, no, I guess this was a .NET Core feature. Sorry about that. This was introduced to basically replace the concurrent garbage collection mode from .NET Framework. And this will collect Gen 2 in the background. This is now enabled by default as well. Gen 0 and Gen 1 are still done on the foreground and will pause the user's threads by default. So these are the different GC modes that are enabled. The one you want to pay attention to if you're building a high throughput application is enabling server GC. So you do that by, I kind of missed my annotation here, by setting the server garbage collection property to true in your MS build file. You can also enable it via an environment variable, and I think there's an app settings.json variable that'll also map to this. But enabling any of those will turn this on. And just to give you a sense of what the performance impact of that is, I took our akka.remote benchmark, which is the configuration file you saw earlier. So this is basically kind of testing the end-to-end messages per second throughput of a single akka.remote connection. Using workstation garbage collection, we were doing about 145,000 messages per second. With server-side garbage collection, we were doing 300,000 messages per second. So that's a 100% improvement in throughput there, just by changing one file in our MS Build project. In terms of all the performance optimization you could possibly do with your application, you are probably not going to get better results than doing that. So you should go ahead and turn that setting on if you're building, it's a ASP.NET applications where where throughput is an important factor. The only real cost to turning on server-side GC is that there's going to be more threads running in the background, and you're also going to be using more memory on average. So if you're building a server farm that has thousands of .NET applications hosted on a single box, you may not want to turn on server GC. That hosting model isn't very common anymore, so you're probably not going to have that issue. But if you do, you're the one user who has to worry about that. Now, as another bonus in terms of getting a lot of performance from just a simple XML change, I wasn't able to work in any slides into this presentation on this because it's a relatively new feature. But one other thing you can do, if I go and grab Sublime here, if you're running on .NET 7 as your runtime or later, you can enable this setting, tiered PGO. This turns on a just-in-time compilation setting called Profile Guided Optimization, which means that the just-in-time compiler for .NET is going to be continually analyzing your application, and it's going to be finding ways to essentially improve your application's end-to-end performance. Primarily, it's going to work on reducing latency is what it's going to try to do. This allows us to do things like devirtualize method calls, reduce interface dispatch overhead, and lots of other little, let's say, .NET internals things that developers like me tried to work around through all sorts of crazy abstractions before. You don't need to do that. The just-in-time compiler will probably do that better for you. The only cost to turning this setting on, and I've got a blog post that addresses this. The only real cost to turning this setting on is the just-in-time compiler works harder than it has to, but the performance benefits usually way outpace this. So if I go back to my slide here, we were doing about 300,000 messages per second with server-side GC turned on. When I have a server-side GC and PGO turned on, we're doing about 450,000 messages per second. So it's definitely worth it. Now, memory allocations are still bad, and the PGO and server-side GC can't get rid of them for you. You as the developer kind of have to manage your own work to some extent when it comes to this. So allocating objects isn't fundamentally a bad thing. You shouldn't prematurely optimize your code and try to get rid of it. What you want to do is avoid sloppy allocations is what we want to try to get rid of, where the allocation really isn't helping you very much. So a good example of this, one major source of allocations inside the older code in akka.NET is delegate allocations. One of the areas where the .NET teams try to improve a lot over with both their compiler tooling and also the just-in-time compiler, so both Roslyn and also the JIT system, is they've tried to help eliminate delegate allocations, but still, it's very easy to create them by accident. So a good example here, this is the mailbox.run method inside akka.NET. This method runs millions of times per second. In fact, if you're doing, let's say, a really busy process, this might run 100 billion times a second, this routine, spread out across all the cores. We had a delegate allocation sitting in the middle of this right here, this actor.useThreadContext. And the reason why this allocates is because we close over the this keyword implicitly when we're doing this. And we were able to go ahead and see that when we were having this actor basically process just messages that didn't really show up on our profiler. We could see that, it took an actor to process, let's see, about 10,000 messages, took us about 215 microseconds. And then, 215 microseconds to just enqueue it into the mailbox, and about 2.3 milliseconds to process them. And we allocated about 21 kilobits of memory when we did this. Well, I went ahead and I inlined the delegate by, rather than just using that sort of method we had before, I took a look at what it was doing and just copied that code directly into this method. This is something that one day maybe the compiler will do for you, but for the time being, it doesn't. So I decided to go ahead and just move that code out of that delegate that we were using and just put it right here in the critical path. Well, one of the things that you'll notice is that we went from having, let's say, 21 kilobits worth of allocations to just 1 kilobit. And the fact that this kilobit value is the same for doing 10,000 messages versus 1,000 messages probably tells you that this is fixed, meaning that whatever is causing this allocation is probably not whatever's happening inside this code. It might be, let's say, some piece of setup overhead that's happening inside the app, because it's a constant size now. It doesn't scale with our workload anymore. So getting rid of that delegate overhead definitely got rid of some unnecessary memory allocations. On top of that, we got a 10% performance improvement because we weren't garbage collecting them anymore. So again, this is like one of those sort of low-level .NET systems programming things you need to be aware of if you care about latency and you want to try to reduce your allocations in order to make the garbage collector not work as hard. Now, there's a lot of other ways to go ahead and try to clean up delegates inside your application. One really useful language feature from C#9, for instance, is you can declare a static delegate now. Which is a useful way of doing that. And you can also declare things like static local functions, for instance. That's another tool that's available. Another really old school technique that people who don't have the benefit of, let's say, didn't have the benefit of modern .NET constructs had to do was either cache delegates or use the expression compiler, where you would go ahead and take a delegate, actually use, let's say, reflection.emit, basically, or something similar to that under the covers, and then cache that sort of what's it called? The .NET middle syntax before it gets to the just-in-time compiler. You would just cache that and reuse it, and that would result in big performance improvements. The expression compiler, you probably shouldn't use that anymore if you're using modern versions of .NET. The just-in-time compiler will do that for you, and it'll do it a lot better and more easily if you do. Ironically, if you use the expression compiler, you probably won't get the benefits of dynamic profile guided optimization. So you're actually kind of screwing yourself over by using this now. However, a couple of other techniques that are still worth exploring for removing delegates. Bartosz Adamczewski, who puts those really good Twitter infographics together on weird .NET compiler optimization. This is one of his hobby horses, using what's called a value delegate. I'll show an example of that in a second. But basically, rather than allocating a delegate, which goes on the heap, you can actually create a little struct that'll basically perform essentially the same functionality and use that instead. That way your delegate actually occurs on the stack, per se, rather than going on the heap and there's no garbage collection. Another technique we can also use to go ahead and eliminate delegates is, rather than doing things like a params object array, let's say for like a logging method, you can actually go ahead and have a bunch of, let's say, extension methods that take generic arguments instead and will produce, let's say, a little generic struct under the covers. That's another technique you can use. And we just implemented this in Akka.NET to improve the throughput of our logging systems front end by about 40%. But let's take a look at value delegates, since I actually have a good slide for this. So this was used to replace a delegate that we would schedule onto the .NET ThreadPool or onto the .NET or to the Akka.NET dispatcher. This is how we'd actually schedule actors to run in terms of the underlying ThreadPool. There was a new interface added in .NET Core 3.1. I think it's the iThreadPool work item. This iRunnable is kind of equivalent to that. But this allows us to go ahead and create a struct that is going to get executed onto the ThreadPool if we want to. So we're going to implement our delegate interface using a value type, and it's going to perform the same work under the covers as a reference type. And we're going to go ahead and execute the work under the covers here. Now, one thing that's worth noting is that casting a struct to an interface will typically cause a boxing allocation. So we may not have actually saved ourselves any real performance hit here. So that's going to be a bit of a problem. But there is a technique we can go ahead and use to eliminate that boxing allocation as well. And if you're not familiar with boxing, boxing is when you take a value type and cast it into an object, and basically it's going to create kind of like a pickled sort of version of that value type on the heap somewhere. It's boxing is typically, if you can avoid it, is basically a sort of example of either sometimes it's sloppy code. In some cases, it's just how do I put this? In some cases, it's sloppy code. In other cases, it's unavoidable. But typically, you want to try to work to eliminate boxing allocations, which, by the way, is something that the JetBrains profiler will help you find, just to give them a shout out. The writer profiler will find. Now, another source of basically wasteful allocations we could try to get rid of are empty collections. Params object is a really big source of these, but also some of our older code in Akka.NET just was kind of sloppy with this stuff. And so we used the JetBrains profiler to find some of this. And I said, okay, this is our state machine that we use for running finite state machines inside Akka.NET. And I'm noticing that every single time we allocate a new state, it's creating a brand new list of objects here, which seems like something it probably shouldn't be doing. So lo and behold, I took a look at the code and this is what's happening here. We're allocating a brand new non-empty array. Every single time we do that, we're going to create 32 bytes. And in Akka.NET, when you have a finite state machine, you create a brand new state object every single time you transition, which can happen quite frequently if you're building, let's say, applications that are handling things like serialization or network handshakes and that type of stuff. So this actually adds up to quite a bit of memory usage over a short period of time. In fact, yeah, it shows that when we were running our benchmark, this produced about 360 megs of allocations. So one thing you can do to eliminate this is .NET now has some nice new handlers, such as array.empty, which will give you a cache generic version of an empty collection that you can use over and over again. And that way you're actually not allocating anything. You can avoid having, let's say, a null list, so you don't have to do null checking, but you also don't allocate any new memory beyond the very first time you use this. This will allocate one 32-bit object everywhere it's used. So this shaved off that entire source of allocations when we did that. And on top of it, it's also castable to iRead-only list, which is useful for us. Castable to IEnumerable, all the other different sort of, let's say, generic collection types, or sorry, generic collection interfaces that you might want to use inside a library of some sort. Now, value types are something that we should spend a little bit more time discussing here, which is that one thing we do inside, let's say, finite state machines is we've been using classes to go ahead and allocate the events inside the same finite state machine class we were just looking at. Every single time we process a message, we generate a brand new event. And you'll notice that we are currently, let's say if I take a look at our slide here, if I benchmark our finite state machine actor versus one of our untyped actors that doesn't use this at all, if I go ahead and blast it with, is this 1 million messages? Yeah, 1 million messages. My finite state machine actor is allocating 287 megabytes versus just the 56 megabytes that my actor is processing. And those allocations are probably coming from things getting queued inside the mailbox plus the message payload itself. But still, our finite state machine actor is doing roughly 5 times as much allocation as our untyped actor. What would happen if I change this to a read-only struct? How is this going to change? Well, if I change it to a value type, you'll see that we've reduced our total allocations by about 30 megabytes here out of the gate. So we're getting rid of a whole bunch of these 32 megabytes worth of allocations here. Now, there's probably more we can do to improve the finite state machine's internals. Probably has more to do with how the message is being processed rather than what's processing. But that's this still right here is like essentially a free improvement here. Now, I talked about boxing earlier. Boxing occurs when a struct is cast into an object, and that can happen in lots of hidden ways, such as casting a struct into an interface will typically do this. Now, unboxing happens explicitly. This is when an object is cast back into its associated value type. So if I cast an object back into an integer, that's going to be unboxing. These are both going to be sources of overhead here. So I think this is still my finite state machine actor. Writer helped me find several problems with this class all in one go. And you can see here, though, I'm comparing the name of my state object, which typically is an enum, usually in Akka.NET's FSMs. I can see that this is allocating 500 megs of memory over time. A method that does not perform any meaningful work, such as a dot equals method, shouldn't be allocating anything. So the fact that this is a pretty major piece of code smell. So I wonder why that is. Well, it turns out that the reason why we were doing that is we were using the default object.equals method under the covers to compare those two state names. And that would box both the, let's say, compare and the comparator every time. So we would have two boxing allocations every single time we did this. So one of the things you can do to avoid a boxing allocation is you can use a generic comparer instead, which basically uses generics to go ahead and perform the comparison. One of the ways you can avoid, let's say, when you convert that struct into an interface, one of the ways you can avoid allocations there is by using generics instead, where basically if you go ahead and cast a struct that implements a generic interface, if you cast that back into the generic interface, that might avoid, not always, but might avoid a boxing allocation there. So in this case, we rewrote the internal equals method, or the equals method on the finite state machine, to use the default equality comparer and to basically have a generic parameter here for whatever the state type is. So that's an enum. This will now be an integer comparison rather than an object comparison under the covers. And that eliminated 100% of those allocations we saw earlier. Now, here's where things get a little interesting, which is that value types are not always necessarily going to be preferable to reference types. This is the envelope type that we use in Akka.net. Every time you send a message to an actor, your message gets packaged inside this envelope along with a reference to the actor who sent it. So these can be generated millions or even billions of times per second inside Akka.net, potentially. It's a read-only struct. And should it be a read-only struct? Well, we did this because, in theory, we thought there should be 0 allocations. Well, if we take a look at our graph here, we can see that for sending, let's say, I think this is 100,000 messages, we allocated about 3.1 megabits of information. And then if we did 10,000 messages, it's about 394K is how much we allocated here. Okay? Well, what happens if I convert this back into a class? How is this going to change the amount of memory allocated by our application inside the same benchmark? Well, the answer is we went from allocating about 394 kilobits to allocating 264 kilobits down below. And similarly, we went from about 3.15 megabytes to 2.1 megabytes. And why might that be? Well, the answer is that struct, because it's copied by value rather than copied by reference, is being created over and over again throughout the entire call chain as it's being passed through the pieces of infrastructure inside Akka.net. And you can avoid that type of copying by using a reference parameter. But some of the internals that we use, such as we use a concurrent queue inside our mailbox, will not support a reference value type like this. It just doesn't support that. So as a result of that overhead, we're going to go ahead and actually see more memory pressure as a result of those structs being copied over and over again. That's very counterintuitive. But if you think that's counterintuitive, it actually gets worse. Let me get through here. Yeah, we talked about copied by value. And one of the things I mentioned here is that if you're going to basically have a referential semantic for your object, meaning it gets referenced by lots of other objects, you're probably better off using a reference type. And that is intuitive and seems like it should be true. However, what happens when we introduce multi-threading into this picture? That benchmark was running on a single thread. What happens when I dial up the memory pressure where those messages are being sent from an actor running on one thread to actors running on other threads? And this means that object is probably going to be shared between different CPUs now. What happens when we use a reference type versus a value type in this scenario? Well, I went ahead and I dialed this up. And when I'm pushing, let's say, I didn't format this nicely in Markdown here, but let's say when I'm pushing 100,000 messages to 100 actors, I'm generating roughly a gig of memory pressure here. And then when I'm doing 10,000, just 10 actors, it's about 100 megs of memory pressure. If I convert that envelope type back into a struct, however, you'll notice that my memory pressure decreases significantly by roughly 30% when I do this. And the reason why that is that even though those copied by value semantics do add up when you're, let's say, working within a single threaded context like how we were before, when you start spanning multiple threads, that overhead gets vastly sort of overshadowed by the amount of actual garbage collection that accumulates, particularly when this is all getting entered into Gen 2 garbage collection probably. Although actually, no, it looks like in this case, it's Gen 1 garbage collection. But still, you can see that we went from, let's say, in terms of the number of Gen 1 garbage collection attempts, we had 225,000. We now have 176,000 here. So we're able to remove quite a lot of garbage collection by moving from being, let's say, a reference type back into a value type again. And the actual performance difference here was pretty negligible in this case. That's because Gen 1 is still relatively fast. So there really wasn't much of a throughput benefit to this change either way. But there was certainly a big memory expenditure benefit by moving things back into their value type. So I just wanted to kind of show that when you're working with, let's say, .NET systems programming, the way things behave in a single thread versus the way they behave in multi-threading is actually going to have a pretty considerable performance impact. And this brings me to the area of pain we're going to deal with next. Threads, memory synchronization, and all the things that basically threads hate about you and your code. Thread static and thread local are very interesting constructs for trying to achieve a degree of memory safety without having any synchronization. This allocates objects directly into what's known as thread local storage. This is basically a facet of the way your operating system kind of allocates memory onto threads, which is that this memory will always be associated with this specific thread, regardless of where it executes. So if I go ahead and, let's say, store a random, let's say a system.random inside a thread local variable, that thread's instance of that random object will be different than another thread happening inside a system. In fact, it's considered to be a good practice to use randoms thread locally. That way you get some differentiation for seed values in a concurrent application. Now, thread local variables are also useful for doing caching and pooling, particularly when you're doing work inside a tight loop, where let's say you have a thread that's going to service a network request coming in from a socket. You want to go ahead and use a thread local that's a buffer for being able to go ahead and perform some work there. And then when you're done using that buffer, you just re-release it back into the thread local collection there. And the reason why it's ideal for this is there's no synchronization. So I don't have to use a lock or a concurrent collection. I am the only person inside this thread who can access this piece of memory. Therefore, it's guaranteed to be safe while I'm working in it. Now, the downside, of course, is that those values can't get shared with other threads, where if you have that requirement, you probably don't want to use this. But if you're doing things in a tight loop, like I mentioned, using a thread local construct for this can be very useful. Now, the other downside of these thread local data structures, like I mentioned, since they're not synchronized, you end up with what we call variants. This means that there's multiple versions of that thread local object floating around inside your application. So for instance, in Akka.NET, we use thread local variables for caching actor paths that have been deserialized. Well, thread 1, if I've got 12 threads that are servicing our remoting system, thread 1 might have a copy of that deserialized actor path, but none of the other threads may not, which means I'm going to have a cache miss depending on who processed that. And that also means I might have 12 copies eventually of that cached object floating around in memory. But the benefit is, if I care about throughput, it's still cheaper to do this and pay for it with extra memory versus having every single worker deserializing messages all have to synchronize on the same cache. Well, this enters into another sort of important area of .NET systems programming, which is the notion of context switching. Reference types passed between threads are going to very quickly find themselves aged into Gen 2 garbage collection typically. In our previous slide, we saw that when I was doing my multi-threaded memory pressure stuff, that they all stayed in Gen 1. That's probably because the application ran very quickly. But if we're doing, let's say, lots of asynchronous work where there's I/O involved and things take a while, the longer that object is rooted, the higher in the generation count it's going to get promoted. And that memory won't get reclaimed until a Gen 2 garbage collection process comes along. Value types that get copied, that are passed between threads are copied, so there is no garbage collection overhead. That's why the memory usage was so much lower in that benchmark when we switched the envelope back to a value type. Well, the other advantage of, let's say, keeping things in thread local storage is that thread local state can potentially be copied from the L1 and L2 cache during execution. You can cache objects that are frequently accessed on the same CPU by the same thread. This is why high performance databases like ScyllaDB use a thread per core architecture. It's so they can take advantage of L1 and L2 caching. This is the memory that's basically held directly by the processor, not by your DRAM, basically. Now, context switching is a really important concept in multi-threaded systems, which is where a thread that used to execute on CPU number 1 is now being executed on CPU number 2. This does things like invalidate the L1 and L2 cache. I can no longer get access to that memory on that cache line anymore. Therefore, I'm going to have to go back and get it from DRAM, which typically operates at a much lower clock speed. So you'll see a noticeable, let's say, increase in lag when that happens. Now, thread locality is this concept I just mentioned about pinning a thread to a CPU. This is what like high performance databases try to do, for instance, where thread 0 is going to get scheduled for execution by Windows or Linux or Mac OS X. And each thread is going to get a fixed quantum of time to do some processing before that thread gets paused and another thread behind it gets scheduled on that CPU. This is how preemptive operating systems work and have worked for the better part of 30 years, is they basically preempt a thread and will let another thread execute so we don't starve applications, right? You don't want your browser, unless you're running Chrome, hogging 100% of your CPU resources, and that doesn't allow your music player or Discord or your IDE to run, right? So each thread gets a quantum of time. Typically on a desktop, that's going to be 30 milliseconds. On a server-side operating system, this value might be a bit lower, might be higher, it might even be configurable, depending on that. But that's how much time typically the operating system will give that thread to do work before it yields. If you don't use your full 30 milliseconds, that's great. It'll go ahead and just automatically, let the thread exit and the next one gets scheduled. Well, when thread 0 completes its quantum, and let's say thread 1 also completes its quantum, other threads are now going to get a turn to execute. If thread 0, now let's say thread 0 has more work that needs to be completed. Let's say you're running like an IAsync enumerable, and so you complete processing a couple of items in your IAsync enumerable, but you exceed that 30 millisecond quantum, you might get scheduled, and the next available thread, or so the next available CPU might schedule the next IAsync enumerable item you want to process back onto a different CPU than you had before. That means that all your thread local memory now needs to be transferred from one cache line to another, and probably pulled from, more accurately, probably pulled from DRAM in order to do that. And so there's an overhead penalty that comes with this. Well, one of the new things they added in I think this was .NET Core 3.0, they added this, is an interface called the ThreadPool work item, which helps avoid delegate allocations for executing on the thread pool. We already know that's good. But it also gives us the ability to actually express a preference for where work should happen in terms of our CPU infrastructure, which this little interface right here, ThreadPool, the unsafe queue user work item, allows me to pass in my ThreadPool work item right here. And sorry, my captions didn't quite line up properly here. But basically what this lets me do, this is the prefer local value. This allows me to say, I prefer this work item to be executed on the same CPU that I am currently executing on right now, if possible. It may not be possible. If let's say that CPU is really busy with a lot of other work that's backed up on it, you might still get scheduled onto another CPU. But this at least tries to go ahead and keep all that work executing on the same context that it was on before in order to help prevent context switching. This can accumulate into a really significant performance improvement inside your system. So we changed, in Akka.NET 1.5, we added dual targeting onto .NET 6 so we could take advantage of this API and a few others specifically. And we can see the before and after performance comparison. This benchmark is running in-memory actors, and I think the number of actors is fixed, but the actor throughput is not. Actor throughput is kind of our own concept of a quantum for processing. This states how many app messages can this actor process before it has to get rescheduled on the dispatcher. So the lower the throughput, the higher the possible amount of context switching we're going to see. So we start with a actor processes messages one at a time versus an actor could try to process 900 messages. The default value is 30 in Akka.NET. That's kind of a sane value. 900 messages would be pretty, you'd have very weird performance characteristics in your application if you ran that. So this is where we had the old high context switching sort of setup. And this is where we take advantage of preferred local in here. you can see that we went from processing about 9 million messages per second to 25 and 27 million messages per second. So a 300% improvement, all from eliminating context switching inside the application. And then if we take a look at some of our other max values down here, I think the highest possible performance we detected using this context switching here is our previous max performance was about 53 million messages per second. Now we're processing closer to 70 million messages per second as our sort of highest possible achievable value. So eliminating context switching, if you can, which by the way, I'm pretty sure that prefer local value. I think things like the TPL will probably do a lot of that for you now, more modern versions of .NET. So you may not even need to actually do anything to take advantage of it. However, if you do a lot of low-level concurrency work, like how our framework does, taking advantage of the ThreadPool work item and that prefer local interface will give you a fairly significant boost to the performance of your application. Now, when we have thread locality without context switching, when thread 0 basically gets rescheduled back onto the same CPU, we can actually reuse the L1 and L2 cache lines that are in that CPU. And that's going to execute many orders of magnitude faster for basically loading the methods you need to call and loading the data you need to do your work than trying to go back to your normal DRAM inside your CPU to get it. That's why thread locality ultimately matters. And that's why context switching hurts. It forces us to operate at a much slower level of I/O than what we could do without when we're executing the same thread on the same core over and over again. Now, data structures and synchronization, I think, is the last thing I'm going to go ahead and kind of touch on. We use inside Akka.NET concurrent queues for managing our queue of work each actor needs to process. So if I have, it's not uncommon for Akka.NET users to have, let's say, several million actors running inside one process. And that means we have several million concurrent queues that are all running, right? Every actor gets its own small little queue of messages to process. Well, one of the things that we know about data structures is that you can actually go ahead and get away with potentially reducing allocations by using linked lists. They tend to be a lot more memory efficient because you don't have to allocate a buffer and you don't have to resize it when it grows and shrinks. You just take your work item and either prepend it to the front of the linked list if it's a doubly linked list, or append it to the back. So we thought, okay, why don't we try using the system.collections.linked list here and see if we can try to beat the performance of the concurrent queue. Now, anyone who's worked with data structures before in .NET knows where this is probably going, which is nowhere good. But we figured, we're computer scientists. We need to try to figure this out, right? Well, taking a look at our messaging performance and our memory performance, we can see that our latency for enqueuing messages is about 200 microseconds for enqueuing 10,000 messages, and you're roughly 10x that for 10x the work. So we're scaling linearly, which is good. And we can see that we allocate about 385 kilobits when we're using this concurrent queue data structure. Okay, not too bad. Let's take a look at what happens if we rewrite this to use a linked list with a lock, because linked lists by default are not thread safe. So this should, in theory, if our theory is correct, offer better memory performance than concurrent queue. And what did we get? Well, just simply, 2.5 times worse performance. And let's see, what was our memory allocation like before? We did 3 kilobits, whereas down here we did, 546 megs. Actually, sorry, I guess we did 3 megs before versus 546. So, just a 1000x degradation of performance. But since we're not JavaScript programmers, we actually noticed that here. So what went wrong there? Well, concurrent queue under the covers is lock-free. Internally, it uses basically volatile members and atomic compare and swap operations. This is stuff as a normal, let's say, .NET programmer, you probably will never necessarily need to care or know about. But if you're the sort of person that writes data structures internally, this is a way of achieving thread-safe performance without having necessarily the synchronization penalty of using a lock. And getting this sort of stuff right can be fairly tricky, but of course, the team at Microsoft and the .NET developers know this stuff through and through. So they're able to go ahead and use these fairly inexpensive techniques for keeping everything synchronized. On top of that, it looks like the internals of linked list are not nearly as cheap as I thought them to be. And in fact, that is the case. The reason being is that they allocate all sorts of little node structures for keeping track of what should be in the linked list with you. This is one area where I'm going to say, if you are planning on using a linked list anywhere in your .NET application, you would be way better off ruling your own instance of this data structure than using the built-in one. The built-in linked list definitively sucks from a performance standpoint and also probably from an easy use standpoint. The only advantage of this I can imagine is that it does work with IEnumerable. Whereas if you write your own linked list where you just use good old C++ style references to other objects, you'll probably get much better performance that way. So I'm planning on doing another updated version of this talk a little bit later this year. We're going to touch on probably a whole bunch of other esoteric performance things like method devirtualization and other techniques for trying to improve performance. But I wanted to go ahead and share some of my pain and some of my experience, some years of working on the low-level internals of Akka.NET. And hopefully you found some value out of this too. And I'd be happy to go ahead and take some questions from people who are attending today now. And also, JetBrains, thank you very much for giving me the opportunity to share. Really appreciate it.
Yeah, thank you so much, Aaron. That was a really cool post. I mean, I guess the thing, or webinar, not a post. But, I'm in the blog. I'm in the blogosphere right now. I'm thinking about blog posts, so apologies for that. No, but you know, the funny thing I was thinking about the whole time you were doing the presentation, right? All these presentations are usually like an hour long, but you mentioned it takes years to figure this stuff out. You know, like how many years has it taken you to like find all these little esoteric improvements?
Well, say that using the dynamic profiler and writer, so just to show you an example here, if I pull, actually, I think I closed the Akka.NET project on my system here because it was degrading my broadcast quality. That's what happens when you load, let's say, an 80 project solution. But basically, when I would run our remote ping pong benchmark, which is where all those Akka.remote numbers came from, that's a fairly complex benchmark because it touches so many other different parts of Akka.NET. It touches our base class actors, it touches our deserialization system, it touches the way we do construction of actor paths. So it's sort of a good like benchmark equivalent. It's like a macro benchmark, essentially, is what it is.
Mm-hmm.
Well, I had the dynamic profiler turned on one time just for kicks, and it highlighted all these issues I had no idea about, like that equals method allocating 500 megabytes of data. I looked at that and was like, WTF, basically. Where did this come from? And I took a look at it, and Ryder kind of really clearly highlighted it and said, like, hey, you're probably doing boxing in here. I'm like, well, sure enough, they're right. And I just knew, and one of the things I did know from experience is like, well, I can probably use since this is a generic class and a generic and these sort of state objects are generic, I could probably use a generic equality comparer here to do this in a much more efficient way than what we were doing previously. And it's one of those things where that's kind of just knowing where to look I'll put it this way. The tooling bringing these problems to your attention probably is 90% of the battle. Knowing the techniques to address them is the other 10%. And it's also kind of a matter of picking your battles. So, for instance, one of the things I wanted to do in preparation for this talk was performance profile Akka streams to see if there's anything to improve in there. Nothing showed up on the profiler that really stood out to me. And it occurs to me that, most of the performance problems that people would probably run into with Akka streams have a lot less to do with Akka streams infrastructure than it does with the flow of control of their application usually. So these sorts of low-level performance optimizations can certainly yield some pretty impressive results. But things like the flow of control of your application, or for instance, where you have I/O and how frequently that's happening, will usually have a much more outsized impact than any of this stuff will. But when you've successfully addressed most of that, that's when it makes sense to go back and look through some of these low-level optimizations, right? So another good example of that would have been, for instance, we made some pretty major performance improvements to some of the internals of Akka.remote. But because Akka.remote today currently has a flow control problem, it has head-of-line blocking, which is a classic flow control problem with TCP, which is what we use. Well, all those performance optimizations that we spent, let's say, probably, a couple hundred engineering hours spread out over the course of a couple quarters, resulted in like a 2% performance improvement. And it's like, that's not very, in the grand scheme of things, that's not a huge, that was not a great use of resources, even though it felt very satisfying as a developer to take care of that. but because the bigger problem is more architectural from that standpoint.
Mhm.
That being said, it does take years to kind of be aware of some of this stuff. And the thing you really want to keep track of is, I'd say, the new developments in the JIT and the new developments in the garbage collector and also in language features will help you address a lot of these much more inexpensively than you used to. All the old techniques, which I learned from people like John Skeet back in the day, around things like using the expression compiler, that made a lot of sense when you were programming for like .NET Framework 4.5. It makes zero sense to do that, in .NET 7 or .NET 8. Not to mention, there's some pretty huge trade-offs that come with that. For instance, like not being able to do AOT anymore, for instance.
Mhm.
So,
Well,
yeah.
I guess that's a good follow-up question, because I was thinking about this too while you were like doing your presentation, right? There's like a lot of good hacks to kind of work around, like .NET is a big abstraction, right? It's a high-level language. The .NET team wants you to use those high-level concepts. But there are times where you can just kind of eke out that performance by using those hacks and understanding the low-level behavior of the framework. Like, how often are you finding yourself going back and reviewing some of those hacks and those workarounds that previously made sense, but maybe no longer make sense and maybe actually are detrimental given where .NET is going?
So we have like two different base actor types in Akka.NET. An untyped actor, which is basically a YOLO actor that just gives you an object and you have to pattern match it yourself. It's as bare bones as it gets.
Mhm.
We introduced probably a year or so into the lifespan of Akka.NET the receive actor, which uses these really neatly compiled delegates that are so strongly typed, easy to reason about. And we use this crazy expression compiler magic internally to make that fast, right?
Mhm.
Well, the untyped actor really needed something more robust to complement it, because we didn't have switch statements for doing pattern matching back then, right? So we had to have this other awful construct to kind of help address some of that stuff. But the receive actor was really kind of a big improvement for the developer experience. Well, that all made sense for probably 6-7 years. But now what problems do we have? Well, we use the receive actor internally in a lot of different parts of Akka.NET, and the receive actor uses expression compilation. That means that the receive actor does not benefit from profile guided optimization the same way the untyped actor does. And I've got a graph that I did like right when .NET 7 came out that shows the divergence of those two, where you can see the untyped actor, when you're running with PGO enabled, is quantifiably faster now.
Mhm.
So it doesn't benefit from that. The other thing that's different is that, when I was building for .NET Framework 4.5, I didn't care about Unity 3D or
You're
Xamarin or these other
Yeah.
platforms that like either barely existed in .NET or used some really wanky version of Mono that our stuff probably couldn't even compile consistently for anyway. You know what I mean?
Mhm.
But now it's like, okay, now these are actually pretty big platforms. We have a lot of people that want to be able to run Akka.NET locally, but using all that sort of expression magic means that we cannot use those components in Akka.NET, which use the receive actor, because it's not AOT compatible. All that expression compiler stuff is kind of antithetical to that. So we probably need to go through and rewrite it to use maybe some newer constructs like a source generator, rather than you're going and, let's say, compiling on the fly these little delegates. Maybe we should just use a source generator to pre-compile it and kind of hide the ball from the end user to some extent.
Yeah, source generators are a really cool optimization that I think a lot of people are still trying to get into. It's still a little difficult to write them, but typically, if you're using a source generator, that's the other person's problem. It's the person who writes it. So
In
for
terms of
you,
writing,
the Akka.NET projects, like, yeah, good luck, and thank you for all the benefits.
well, in terms of if you did a Venn diagram of like people who enjoy regular expressions and people who enjoy writing source generators, I think it'd be like a flat circle like that.
Yeah.
Yeah.
I guess let's see another question. I noticed something. This maybe not a question, but I noticed uh when you were doing a lot of the generic constraints to kind of remove that boxing effort. I wonder if you could see those changes and maybe track down those problems a little easier now that Rider has like high level and low level C# in our IL viewer. So sometimes you write high level C#, but it gets lowered to like lower C# constructs. I wonder if you could find those issues easier by checking the IL low level C# that potentially gets generated, right? Because sometimes in C# you're looking at code and there's a lot of abstraction, hidden things happening, and you're not essentially seeing it. So I wonder, like, as you go through and improve Akka.net, maybe if those kind of tools could help you and your team kind of find those things faster.
We have a lot of people that like using IL Spy and things like
Mhm.
that for trying to get into the guts of it. And what's the name of the website where you can get the IL for a .NET method? It's not .NET Fiddle. It's something else.
Yeah, I know what you're talking about. I forget what the name is. If anyone in chat knows, please put the link there.
But
I'm sure Martin's in there.
we'll
We'll
get some
find
of our open source contributors. We'll go ahead and be like, yeah, we can improve this, and like here's what this IL looks like here, and here's what it looks like if we change this around. Now, one thing I would caution about doing that, Sharp Lab. There you go.
Sharp
Thank
Lab.
you.
Yeah, there we go.
One thing I would caution about doing that is you can screw yourself over in a major way by trying to go after those crazy optimizations, because that's exactly the sort of thing that the just-in-time compiler and Roslyn might fix in the next release.
Mhm.
So I would argue that probably the safer approach is sticking with simple constructs that can be optimized easily down the road.
Mhm.
Now that being said, you still should doing some stuff like eliminating, params, object allocations with like generic overloads. That's something that you're still going to need to do on your own. That's, even though that's a quote clever optimization, it's still going to need to be there in order to eliminate boxing and to eliminate unnecessary array allocations, and also to kind of help give you, let's say, a little bit more control over how the internals of that method really allocate under the hood. But doing things like trying to optimize for what the IL looks like on this version of .NET this year, knowing there's going to be another one next year, might be, might be a way to attach yourself to the technology treadmill in a major way. You know what I mean?
Yeah, that's a really good point, right? Like, the .NET team members are making decisions about what ultimately gets turned into IL. So it's like, it's .NET's supposed to be a high level language, like platform, and C# supposed to be a high level language. So when you find yourself in the low level aspects of it, you might see benefits, but those might be undone by kind of what the .NET team is attempting to do later. So that's a really good point. I guess one last question. I think a lot of people have been asking. There's a school of hard knocks, which is kind of what you've learned a lot of these things through. But are there like blogs? Are there books? Are there courses that you could recommend for folks to kind of learn this stuff, or is it just trial by fire?
There are some good books, and there's been some that have been very helpful to me over the years. I don't know if there's a new version of this in print. This is back in like the ASP.NET MVC3 days, but there was a book on high performance ASP.NET.
Mhm.
And it was some Rocks book. I can't remember the exact name of it, but if there's a version of that for .NET Core, you should definitely look at it. They talk about taking advantage of things like donut caching and all these other techniques for trying to reduce I/O. And that's, if you're a web application developer, that's like a very practical book. It's not about how to eliminate boxing. It's like, no. Here's how you make sure you don't have to do unnecessary round trips to the database and things that have like a much more visible impact on latency and that type of stuff. I would start with a book kind of focusing on that. Now, if you really want to get into some low level stuff, let's say you're building like scientific instrumentation, which, a lot of people in our community do that. They are responsible for, let's say, firing lasers and reading the output back really quickly, all sorts of crazy stuff like that. A book that I have a copy of, and I'll admit that a huge chunk of it is over my head, is Konrad Koska's Pro.NET Memory Management.
It was just mentioned in chat. I also have that. It's a pretty big book. So I also like his intro. There's like a couple chapters in the beginning just talking about the history of computing. So even that alone is actually a pretty good read, even if you don't get to the deep .NET mechanics, I guess.
I mean, he gets into some stuff I've never dealt with, like pinned memory, for instance, is something that I've never really spent much time working on myself. That's another one I'd recommend. I think he also has a course, Pro.NET Memory or something.
Yep.
He has an online course you can take. That's a good one. In terms of other general knowledge programmers should arm themselves with, setting the .NET facet of it aside, a computer organization course would be very helpful. Which is I have a computer science degree, so I learned this in college, but you can find samples of this on Udemy probably, which is learning about how does the actual organization of my computer's hardware function. Like, for instance, how does this console.write line actually translate into bytes that are going to be executed by the CPU? And this makes you more aware of things like instruction sets, how CPU caching works. Makes you aware of what the significance is between a 32-bit and a 64-bit architecture. You don't need to be, electrical engineer learning how to implement the MIPS instruction set using your own logic gates and all that sort of stuff. Like, more power to you if you want to go down that road. But kind of understanding conceptually, here's how assembler works, here's how bytecode works, here's how the operating system works from a scheduling standpoint. Here's the whole notion of like a preemptive operating system versus a real-time one. If you do IoT, you're going to run into a real-time operating system at some point. That's how things like brake controllers and guided missiles are built. But those are all learning that sort of stuff kind of helps you be mindful of, okay, I need to be a little aware of how I'm, let's say, scheduling work or how I'm spinning up threads if I'm manually managing them, because there's a point of diminishing returns where adding a new thread per work item is going to very quickly result in nothing getting completed, right?
Yep.
So being mindful of that. I guess the other area that's worth focusing on in terms of .NET performance, so we talked a bit about memory, talked a bit about low-level sort of bytecode level instruction stuff. Probably the more practical one out of even all that stuff is actually concurrency, which is how do I take advantage of multi-threaded programming? Probably the most accessible means of doing concurrent programming in .NET is going to be the task and parallelism library. It's async and await, right? I would think a little bit about task decomposition. I would also reason about what's the benefit of a non-blocking task versus a blocking one. One thing that the .NET tooling will usually flag is when you have a non-blocking task. Well, there might be a good reason why not to do that. Maybe not necessarily everything needs to all complete at the same time, or maybe you want to be able to kick off this detached task and have it come back later. Akka.NET would be a good technology to actually learn for being able to do, like, in the scope of, let's say you're not trying to build a distributed application. Let's say you want to do something simpler, like take data coming from a server and display it in the Maui application. Akka.NET would actually be a good piece of technology for learning how to do that. So I would learn how to basically reason about those sorts of constructs, because that's probably going to get you more bang for your buck as well. In terms of other courses I'd recommend, I can't really think of one. Is it John Skeet's book, C# in Depth?
Potentially. I don't remember back that far. I'm getting old, Aaron, so my memory's starting to get a little fuzzy, but I do remember he did write a book. I forget the title of it though.
And they're mentioning in chat Andrew Ashkins, who's one of the authors of Benchmark.net, Pro.NET benchmarking. Benchmark.net's a very good tool to learn. I would caution, well, let me rephrase this. We use Benchmark.net probably gives you the best results when your benchmarks are fairly tight in scope, when you're basically trying to test, let's say, a relatively small number of things all working together. We do use Benchmark.net for some macro benchmarks where we start including things like network I/O in the picture. But the amount of clarity you're going to get from that and how consistent the results are going to be is going to change a lot when you start doing that.
Well, I think during your talk too, you even showed like the difference, right? Like you thought you optimized something and the benchmark showed that it was like better in that like single threaded scenario, but once you started adding multi-threading, that next benchmark showed that no, there's actually a performance degradation, right? So it's really important to test as many scenarios as you possibly can, and to test early and often so you don't kind of like code yourself into a corner and can't kind of find your way back. So I think that was kind of like a really important lesson I gleaned while I was kind of watching your presentation. So
absolutely. When you add multi-threading is a dimension that's got something that looks fast in a single threaded context might be radically different when you start multi-threading. So I kind of recommend using a combination of micro and macro benchmarks. For macro benchmarks, we just kind of roll those ourselves using a console app.
Console apps are great, and don't say anything bad about console apps.
Yeah, don't knock them, man. As long as As long as basically they are consistent at basically as long as what they're measuring can be reproducibly consistent, then you don't need benchmark.net necessarily.
Yeah.
What benchmark.net will give you a lot of insights into is the super low level, like really quick stuff. Like if I want to know what the nanosecond difference is between this for loop structure and that one, I'm not going to figure that out in a console application I wrote myself. Benchmark.net will tell you that.
Yeah. So Douglas Kroll asks, are there good talks and high-level overview of the architecture of Akka.net? Well, I know, Aaron, you have, I think you have a boot camp or a course that people can sign up for.
We do. We have the Akka.net boot camp, which if you go to learnaka.net as the URL for that, that will give you access to it. If you go to the official Akka.net website, there's links to it in there as well. I think at the footer of the website. Or our GitHub, I think our main GitHub organization page has a link to it on there. That's a good place to get started with kind of learning about the basics of Akka.net. You can kind of capture it through there. Now, if Doug was asking about, let's say, how we architected the internals of Akka.net, you're probably going to have to look at my blog for some of that stuff. I do have some blog posts and YouTube talks about it. We're just soliciting input on my Twitter today. If we're trying to rewrite our CQRS system to be able to support millions of, well, not millions, but hundreds of thousands of concurrent queries. And as to say, hey, we're talking about all of the back pressure issues you have to deal with when you do that, which is a kind of this is like not a low-level .NET, but like a high-level architectural problem. If you're interested in learning about that sort of stuff, definitely give me a follow on Twitter. I talk about all sorts of esoteric issues that relate to it is esoteric and idiosyncratic architecture problems that come up there.
Well, I guess this is a good segue to kind of wrap up. Again, thank you so much, Aaron. Let me do the closeout here. Thank you, everyone in chat. The chat was awesome today. I always love talking to the chat, folks. So if you want more information about Rider, you can head over to jetbrains.com/Rider. You can follow us on Twitter. We also blog a lot about .NET. Martin, the other advocates, and I usually blogging about .NET. So go over to our blog. There's a lot of good content there. If you want more YouTube content, you can head over to JetBrains TV. Aaron mentioned, be sure to follow him on Twitter. His Twitter handle is Aaron on the web. And you can read his blog at aaronstannard.com. Also, this is where I beg and embarrass myself for likes and subscribes. So if you really enjoyed this content, you enjoyed this webinar, and you want to see more of this stuff, please head over to our JetBrains TV channel where you can subscribe, hit that bell, give me a thumbs up, maybe leave a comment, leave a nice comment. I really like those. You can leave a mean comment too. I've gotten those too. So whatever you like. Other than that, that's really it for today. Again, thank you to our guest, Aaron, and we'll see you folks next time on our next webinar.
Thanks for having me.
Yep. Thank you.